Hello, class, and welcome to Researcher TV, where learning research is made easy. And now we are on part two of our data analysis, presentation, and interpretation. So, if we will review what we have learned from part one, we actually discussed on the preliminary activities that we need to do prior to data analysis. And that includes ensuring that all of our data are consistent, all of our data are correct, exact, finding the right statistical tool based on our study objectives, and then considering all the ethical considerations or putting into the ethical considerations prior to data analysis. And of course, identifying the type of variable that we are going to process or analyze, or the type of data that we're going to analyze. And then we discussed about descriptive statistics, wherein we learned about the role of percentage of your central tendencies or your mean, and then the significance of standard deviation as well in terms of how data are dispersed or the nature of data. And now we are done with our descriptive statistical analysis. Let's proceed to inferential statistical analysis. So let's begin by understanding the word inferential. So when we say inferential, we are trying to make an inference. And inference is similar to predictions or generalizations. But these generalizations or predictions are geared towards the characteristics of your population. Okay. And these predictions are based on sample data. That means not all or only a portion of the population were extracted or were um, uh, a portion of the population were given the tool or were tested or were evaluated or surveyed. And then the data that they produce is the one or are the ones that are going to be processed and analyzed. So basically, it's just making predictions or generalizations from a portion of the population. So given that analysis or given that idea, it is important to take note that inferential statistics is only done on a sample data. Okay. So if you deal with the sample data, automatic, you are going to do an inferential statistics. But sir, how about if we have, let's say, if we do a census or a total enumeration? Now, in this case, inferential statistics may not be applicable because you already covered the entire population. So because it is already the entire population, no need to make an inference, but rather the appropriate data analysis for that will just exclusively be descriptive. Because in descriptive, you're already discussing the entire or presenting the entire characteristics of your population. Okay. Now, so we are clear with that. Okay. Now, when we do inferential statistics, there are specific um, interactions, okay, that we are interested to explore or evaluate. And that includes significance of relationships or correlations, differences, and even associations. So depending on your study objective or your study goal, the type of interaction or variable interaction that you are going to establish or analyze will depend on your goal. So, for example, if your goal is to uh, test whether the two variables have correlation or association, then there is a specific inferential statistical tool for that. If you wanted to compare and contrast parameters based on groupings or based on how you're going to categorize your data, then there's also a specific statistical analysis for that. So in the later part of this discussion, we will be presenting or we'll be learning about these different kinds of tools, okay, based on the specific purpose of what you wanted to establish, okay, in relation to your study objectives. All right. Now, we have to remember that inferential statistics provide a strong evidence in terms of how your sample data would actually provide or would project um, a prediction or a generalization to the population. So it's really very important that we have to conduct or undertake your inferential statistics very, very careful. Okay. Now let's proceed to the key components. So these are the important things that we need to know and be familiar when we do your inferential statistics. So number one is hypothesis testing. Yes, hypothesis testing. This is non-negotiable. In any inferential statistical analysis, there is always hypothesis testing. Because remember, okay, it is in every inferential problem, there is always hypothesis testing. Okay. Now, if your specific research objective is plainly on, let's say, just description, then no need to make a hypothesis because, as we know, if you will recall our basic concepts and hypothesis, it is a tentative answer to your questions or to your specific research problems, specifically to your inferential questions. So these are only related, or you can only come up, okay, with hypothesis only for inferential questions. And remember that all inferential analysis requires hypothesis. So that is our main mantra, okay, for this discussion, that all inferential analysis require, okay, hypothesis, right? So hypothesis testing involves formulating a null and alternative hypothesis about a population parameter or a variable of interest and using the sample data to assess the likelihood of these hypotheses. But in most cases, class, we actually use just the null hypothesis, okay? We seldom use the alternative hypothesis, but in most academic researches or even with undergrad or basic education research, we always recommend the use of a null hypothesis. Why is this so? Because the null hypothesis is also known as your statistical hypothesis. Most statistical analysis are based on the acceptance or the rejection of your null. Okay. So the null hypothesis is what we're going to use. So it's always going to be no difference, no significant relationship, absent of the cause and effect relationship. It's always null. Okay. Now, common hypothesis tests would now include your t-tests, ANOVA chi-square tests, and of course your regression analysis. So let's try to look into these tests later. Okay, as we learn the characteristics of these tests and what are these tests for? Where do we use these specific tests? Okay, there you go. All right. Now, remember that hypothesis testing provides a framework for evaluating whether observed differences or relationships in the sample are statistically significant and not only due to random chance. Okay, so significance would mean that it's consistent, it is valid, okay, it is accurate in a way, and it's not just only because of some random chance that there's a difference or there's association. All right. Now, another key component that we have to take note or remember is your confidence intervals. Now, your hypothesis testing must be placed or must be positioned according to your confidence intervals. And usually, your confidence interval is researcher identified. So it's up to you how much confidence you're going to set in terms of the the accuracy of your and the certainty of your results, okay, or of your analysis. So it provides a range of values within which the true population parameter is likely to fall to a certain level of confidence. So that means if you have a 95% confidence interval, you are 95% confident that the true population parameter lies within the specified range. Now, usually we do a high confidence intervals if we have a high or if we have a large sample size. But that's not always the case. Establishing a high confidence interval will actually provide a strong support, okay, strong validity and accuracy and reliability support to your findings. So we usually use the 5% confidence intervals. So that means the remaining 5% is your margin of error. Now, I think you've heard about it or you're familiar with that one. So the 5% margin of error or transpose in decimal value of 0.05, that is our rejection area. So if our p-value or probability value, later we're going to talk about it, falls falls in the rejection or in the margin of error, that means we have to accept the null hypothesis. So don't worry, we will be uh, going through the hypothesis testing in detail later on. Okay. Mhm. And then there's also what we call your effect size measure. And this quantifies the magnitude or strength of relationships or differences observed in data. So usually it is statistically solved as well. And this one provides additional information about the practical significance or the importance of the observed effects beyond the statistical significance. Usually your effect size will depend on the quantity of your samples or your respondents. So for example, if there is a significant difference along a large sample size, its effect size would also be larger as compared to another study that has no significant difference but with a smaller sample size. All right. Okay. So don't worry, we'll not be really dealing with effect size measures, probably in our next video or next discussion, but just a nice to know information about these components. Okay, so I guess we are now ready to learn about the common inferential statistical tools. Now, what we'll be presenting in your class are parametric statistical tools. So this means, if you can still remember from our previous lesson, parametric statistical tests need to accomplish, or you need to fully assume three assumptions. Okay, so number one, your data should be continuous. So your data should either be interval or ratio data. Number two, you need to have a large sample size and it should be randomly selected, right? Because random selection would mean that there is no bias. Yeah, bias is eliminated, and the possibility of purposive selection is also avoided. And then the third and the most important assumption is the normality of your data. So data should be normally distributed. What do we mean by normally distributed? Normally distributed, if you're going to plot it in for example, in a scale, or it looks like a bell-shaped distribution. That means the mean is at the middle, and then there is somehow an equal distribution of data above and below the mean. So there is no skewness. So that means the data is not clumped together below or above the mean. And then there is no kurtosis as well. That means very, very few or no outliers. So that's a normally distributed data. So if you have a normally distributed data, large sample size that is randomly selected, and a parameter that is continuous, then you're up for a parametric statistical analysis. And these are the examples. Okay, so let's assume your data is your data fulfills the parametric assumptions. So let's get into this. Okay, so the first one is your t-test. So this is really very familiar. Now, before we begin, there are actually two types of t-test class. So the first one is independent t-test and your dependent t-test. So independent t-test, or two means, okay, two groups. It means that you're going to compare, okay, if there is a statistical difference between two groups or condition. But in independent t-test, you have two groups. So two groups providing mean scores for each. So you have two mean scores or two means from two groups. Okay. While t-test for dependent means, you have two means, but it is only provided, or you only get it or extracted that from only from a single group. Now, usually the dependency test follows a pre and post test. So, for example, if you have an intervention and you wanted to know whether the intervention is effective or not, you will measure the parameter before the administration of the intervention, and then you're going to measure again the parameter after the administration of the intervention. And then you're going to compare the means before the intervention and after the intervention. And that becomes a t-test for dependent means. Okay. Now, remember that the p-value, so I mentioned about the p-value a while ago. The p-value associated with the t-test indicates the probability of obtaining the observed results by chance. There. And remember that the t-test only compares two groups, but if you will have more than two groups, it's going to be a different test. And it is used when the variable of interest is continuous and approximately normally distributed. So, yeah, so this one explains the parametric requirement for the use of t-test. So it calculates a t-value which measures the difference between the sample means relative to the variability within the groups. And the p-value, okay, so we mentioned the p-value here. The p-value represents a probability of observing the observed results more or results more extreme under the assumption that the null hypothesis is true. There. So remember that it quantifies the strength of evidence against the null hypothesis. So therefore, a small value, usually below a predetermined significance level, so that is your margin of error or level of significance, the 0.05 is what I've mentioned a while ago, suggests a strong evidence to reject the null hypothesis. So if your p-value is equal or less than 0.05 or your predetermined significance level, then your decision is to reject the null hypothesis. Okay. However, a large p-value indicates weak evidence against the null hypothesis, suggesting that the observed difference could be due to chance only and not because of the true and accurate data, behavior, or characteristics. So how do we accept or reject hypothesis here? So the hypothesis testing, the null hypothesis assumes that there is no significant difference between the groups being compared. If the p-value is below the chosen significance level, therefore the null hypothesis is rejected, equal or lower than. And rejecting the null hypothesis implies that there is an evidence to support the alternative hypothesis, which states that a significant difference exists. And otherwise, accepting the null hypothesis means that there is insufficient evidence to conclude that indeed a significant difference exists between the groups. So let me give you an example. Let's say your hypothesis is there is no significant difference in terms of plant growth, okay, between the control and the experimental group. So let's say your control group is the one that you don't put your fertilizer, like for example, your treatment variable is a customized plant fertilizer. So you don't obviously your control group does not receive your treatment, and then your experimental group or your treatment group receives the treatment. So you wanted to know whether there is a difference on its growth in terms of, let's say, number of leaves and length in centimeters, for example. And we wanted to compare whether there is indeed a difference between your treatment and your control. So your hypothesis is there is no significant difference. And then your p-value is at 0.03. So that is less than your significance level. So what is our decision? Reject the null hypothesis. So we come up with an interpretation that it is significant, there is a significant difference. Hence, our conclusion is there is a significant difference between, there's a significant difference in plant growth between the control and your treatment group. But of course, to supplement your conclusion, since you have already established that there is a significant difference, try to go back to your descriptive findings or results, and then try to look into your you try to look into your how do I say this mean. So whichever group has the higher mean obviously would have a that would have I mean the treatment variable is effective towards the group that has a higher mean. Right? There you go. Okay. Now, what about analysis of variance? So, ANOVA is a statistical test used to compare means across three or more groups or conditions. So, if you have more than three groups or conditions, then you are going to use your analysis of variance. There are a lot of types of analysis of variance, but let's just focus on the single factor analysis of variance, the most commonly used ANOVA. So ANOVA partitions the total variation in the data into two components, variation between groups and variation within groups. So between groups, that means one group compared to another group, and then that group compared to the rest of the group. Okay. That's why your ANOVA becomes a little bit complicated or complex because you are actually, or we are actually establishing which pairing or which comparison creates the difference. All right. So we're going to discuss about post hoc analysis in a while. So ANOVA calculates the F value, which represents the ratio of the between group variation to the within group variation. Okay. So just like a p-value indicates the probability of observing the obtained results or results more extreme under the assumption that the null hypothesis is true. Okay, so it's still the same. So our accepting and rejecting the hypothesis in ANOVA is similar with t-test. But here is the difference. If there is a significant difference, okay, we have to do another test, and that is your post hoc analysis of means. So what is this? The purpose of your post hoc analysis is to determine which among or which pairings of the groups created the difference. So what we usually do is we pair a specific test, like I kind of like forgot the specific post hoc tests, but those post hoc tests will establish which pairing would created the difference. I mean, so for example, treatment A and for example, group A and group B. Group A and group B, there's no significant difference. And when I pair A and C, there's also no significant difference. But between B and C, there is a significant difference. So even though some of the pairings do not yield significant difference, okay, as long as there is only one pair that creates a significant difference, then the entire hypothesis will, the entire null hypothesis will be rejected. Okay, there we go. And just like that, you could also go back to your descriptive data to establish which specific group would actually have the difference, or in terms of its values for that certain parameter you have identified. Okay. And last but not the least, under our common inferential statistics is our correlation. So correlation coefficients are used to measure the strength and the direction of the relationship between two variables. So this is interesting. As a researcher and as an advisor and as a mentor, I am really fascinated with correlation analysis because it's very interesting to note where the relationship is heading, or the direction of the relationship, and also how strong the relationship is. All right. So here, in correlation, just like with your ANOVA and your t-test, there is also p-value. So if the p-value is within, falls under the rejection area or below your significant level, then you have to reject the null hypothesis. But obviously, usually class, by looking into another, okay, another value or another index or another figure in your analysis, in your SPSS results, will actually tell you whether you're going to reject or accept the null hypothesis. And this is your correlation coefficient. Now, it's pretty obvious that if the p-value is, or I mean, if you reject the null hypothesis, there is a significant relationship, right? So the next thing that you're going to do is you're going to look into the correlation coefficient there. So unlike in your ANOVA and your t-test that you have to go back to your descriptives and look at the means, okay, of the group, all right? In your correlation coefficient, this will now tell you the direction and the strength of your correlation. So it ranges from -1 to +1. And a positive correlation coefficient that means from 0 to +1 indicates a direct or positive relationship. That means if one variable increases, the other variable also increases or vice versa. So both variables head towards a certain direction. So if one goes up, the other goes up as well. That is for a positive correlation coefficient. However, a negative correlation coefficient suggests otherwise. It is an inverse or negative relationship. So when one variable increases, the other variable does not increase, but rather that variable decreases. It goes to the opposite direction. Okay, so that is the difference between a positive correlation and a negative correlation. How would you know if it's a negative correlation? If the coefficient has a negative sign. So it's a -1 to 0. Okay. And also, take note of this. In order for us to determine the strength of correlation, the closer the coefficient to -1 or +1, the stronger the relationship is. Yes. Okay. So in here, I'll just show you three levels of level of strengths of correlation. So for a weak or low correlation, that's between 0 to 0.3. By the way, I forgot to mention a correlation coefficient of 0 indicates no linear relationship between the variables. For a correlation coefficient that is really close to 0, that means no linear relationship. So most likely you're going to accept the null hypothesis. Your p-value is greater than your significance level. Okay. Now again, weak or low correlation is 0 to 0.3. Then 0.3 to 0.7 is considered moderate or moderate to high, while a correlation of 0.7 to 1 is considered strong or high. All right. So just like that, okay, I think we've already mentioned that this is how we're going to interpret your correlation based on the direction and the strength or the value of your correlation coefficient. But remember, it is important to note that correlation does not imply causation. Yes, it does not imply causation. A significant correlation does not necessarily mean one variable causes the change of the other, because the nature of the behavior of the other variable is only affected, not necessarily affected, but there is a certain association or correlation between the two. But again, it does not imply causation, right? And the interpretation of correlation coefficients may vary depending on the field of study and specific research questions. So the one that I've shown you is the typical 3-level strength, but in some studies or disciplines, they would actually have more ranges, and it would have from very low, moderate, high, and very, probably like 5 levels of strength. So it really depends on the discipline and the type of research question that you're going to establish. Okay, so my goodness, our discussion on inferential analysis is kind of long, so I'll probably make a part 3, which is on data presentation and data interpretation. So once again, thank you very much, class. This is your Sir Searcher, and we will see you on part 3. Thank you.